Hello. So this is a video that goes over the material that we presented on the second R help session. So the main purpose of this R help session was to address some issues that students have with downloading files from MyStatLab, for example, and then importing datasets into R. And then also the other part of the R help session also covers how to approach building a linear model. So in that sense, it is a somewhat repetition from the material from the first R help session, but it was given as an extra session just in case any of you had any questions. So first of all, I wanna bring your attention to this here. So basically, everything about the course and especially some code in R you can find on this page. So keep that in mind whenever you have any issues with code or you don't remember how to do anything, then you can just come to Canvas and then go to this course website. So this other version of the course website. So the other thing that I want to do before going into RStudio is just to show you guys how to download datasets in MyStatLab. So for example, I hope this question has a data set. So for any question that has a data set, you just have to open the dataset and then click the small Windows sign. So here, for example, in this question, in the homework, you can open the dataset by using this here, and then click Open in Excel, and this will download the Excel version of that file. Now, however, in RStudio itself, you can import the data as an Excel file or a CSV file. Now let's go over importing the dataset as an Excel file, which you can do in two ways. So you can import it either by using this here, this option, so import dataset, and then you go from Excel, and then you browse and you find your file, or you can do it in code. Now before we go into that, I'll do that for you as well. Just to demonstrate, first I want to make you aware of the working directory. So basically the working directory is the folder within your computer where R will look for the Excel or CSV file that you want to open. So basically the working directory, if you set the working directory at the start of each R script, then you won't need to set it, and you can just import the data files just with their name and the extension. So the way to set the working directory, or you can think of it as the default folder where R will look for files, is with this code, setwd, and then you have to find the path. How to find the path? So you can go to Files here, and then you can go to Home. So I'm working on a Mac. On a Windows it will be very similar. It will show you the disk drive, C, D, or whichever one you're using. So on my computer specifically, I want the working directory for this help session to be in desktop, and then stats371G, and then our help sessions. Now this is basically the folder that we want to set as our working directory, and you can find the path file right here. So if you hover over our help sessions or the folder, you can see the path file appears, and you can write that down here and execute that command. Another way to do it directly is once you open the folder here, you can click More and then set as working directory, and you can see the command itself appears here in the console. So you can just copy that over here in your R script. So that's two different ways to set the working directory. And I've shown you how to download from MyStatLab. So now let's go ahead and go over the importing of a dataset, more specifically of an Excel file. So just this command, I want to go over what it means. All the functions in R, all the commands, if you like, such as plot, such as lm, such as summary, so on and so on, are part of libraries. Now, libraries are like collections of commands. Some of these commands or libraries are already loaded into R when you open it. So, for example, plot is already loaded. You don't have to open the library. But for some, you have to call the library, open it in R, so that you can access the commands that are a part of that library. So this is how you do that with the library command, and then inside you put the name of the library. So it turns out this command read Excel is part of this library. So here I'm just making sure that I'm importing that library first before using read Excel. Now, read Excel might be also included already in R, but I just wanted to illustrate this command library because later on we'll have to use, for the other homeworks and assignments and your projects, you'll have to use some libraries that are not included when you open RStudio. So let's import the Excel file. There's two ways. So you can either use the code that I've written here, or you can use the import dataset command in the environment here on the upper right of the window, and then you go from Excel. If you were to import a CSV file, then you would choose the first option, from text base. So if you go from Excel and then you browse, and then I go to my R help sessions and I want to import motorcycles.xlsx. And I click open. So now be careful, here there's an option that you should always check. This command here, it says first row as names, will dictate whether the first row of your dataset will be saved as names or titles for the different columns, or if it's going to be saved as part of your dataset. Now, if this is clicked, if this is checked, obviously the first row will be considered names and it won't be included in your dataset. In this case, in our dataset, yes, the first column is indeed names, so that should remain checked. But in some instances, although they might be rare in this course, in some of them you might not have the titles, so this should be unchecked then. So you just go ahead and click import, and then we can see our motorcycles dataset is imported right there, and it opens right here by default. And down here we can see the command that was used to import it. Now you can see that this command down here is a bit different than mine, and in three main ways. So first of all, I save it in this text here, I save it as raw data. So because if you just import a motorcycles Excel, it saves it as a motorcycle. So I just save it as raw data. And then I use the equal sign instead of the arrow sign, which is valid. You can use it whenever, interchangeably with the arrow sign. And then inside here, I have another command, which is column names. Now this column names is equivalent to the box about titles, column titles that I showed you before. If this column names is true, then that means that box is checked, or in other words, that the first row of your dataset is titles for the different columns. Now if we run this, we can see we get raw data right there. So now that we have the data, let's go on to building the model. Whenever you do a linear model, for now only a simple regression, but later on you'll do also multiple regression and a logistic regression, so on. For linear regression, you have to first plot the data. Now, when you plot the data, the thing that you're looking for is whether the data follows a linear trend or seems to be following a linear trend. If we observe that the data is following a linear trend by observing the plot of the data, then we go ahead and we create the linear model. Now here is a way to plot. which I'm sure many of you have already seen. So I want to, let's say, just for argument's sake, just for the example used in this our help session, let's say that we want to predict the MSRP from wheelbase. So I can plot it in this way. Another way to plot it is to have, so instead of this command, we can have the following. So we can have plot, and then we can write the name of the variable, MSRP, tilde sign, so the response variable or the y variable, tilde sign, then we will have the x or predictor variable, and then we put data equals to raw data. Now be careful, what's the difference between the two? When we write the first version, then we write what we want plotted on the x-axis, comma, what we want plotted on the y-axis. In this version, which is similar to the LM statement, we have to write the y value, then tilde sign the x value. And then the tilde sign, you always remember it, you can think of the tilde sign as a function of. So MSRP as a function of wheelbase, and then comma, we give it the data set where to look for. Because if you notice here, I don't use the dollar sign as in the previous case, which means R will not know where to look for these titles, where to look for these variables. So that's why we put a comma and then specify. So the data is found in the dataset raw data. So if we execute that command, you can see we will get exactly the same plot of the same data. Okay, so now once we learned how to plot and we see the scatter plot of the data, let's say, just for the sake of the example, let's say we conclude that it's a linear relationship, although it seems a bit curved. But let's conclude it's a linear relationship just for the purposes of illustrating. Let's go on and produce the model. You do this with the LM statement. So always when you use the LM statement, you want to save it. You want to save the model under some name. Now here I save it as model. You can save it as under whatever name you prefer. So I put model equals to LM, and then inside parentheses we have to give it the arguments. The LM statement always has to be written with the tilde sign, and I will stress that it's never advisable to use the dollar sign notation inside the LM statement, because when you try to calculate confidence or prediction intervals, then you will get multiple values and it will get very confusing. So always when you use the LM statement, please just use the name of the variable, of the predictor variables or variable, and the response variable, and then comma, data equals to the name of your data set. So that is the format that you should always use for the LM statement. That builds our model and saves it as model right here in the environment, we can see. And then summary, basically summary of the model, gives you all the important information of the model. So let's just quickly review some of the things. You will get familiar with more and more of these things as time goes on throughout this course. So first, you have some statistics about the residuals, the quantiles, so minimum, medium, max. And then you have some information about the coefficients, which is very important for you at this point. So here you have basically the estimates, which are the estimated values of the slope of wheelbase, or the slope that multiplies wheelbase in the regression equation, and the intercept. Then you have the standard error of both of those parameters, or you can think of it as the standard deviation of the parameters. The t-value, the t-statistic, which you will get to later. I'm not sure if you will cover it in this class, but this is the t-value or the t-statistic correlated with the two estimated parameters. And then you have the p-values. So this is the p-value, which you can use and you will use in the course to estimate statistical significance, to say whether something is statistically significant or no. And then down here you have the residual standard error, or the standard deviation of the residuals, the degrees of freedom. You have multiple and adjusted R-squared. For now, you have to pay attention to the multiple R-squared. That's the one you're interested in. you will get to adjusted R-squared when you do multiple regression. And then you have an F-statistic for the overall test, and then a p-value for the overall test. So that's basically the output of the summary statement. Note that for now, I will repeat, you will mostly use the slope, the intercept, the p-values, and the R-squared. After you build your model now, you want to check all of the different assumptions. By building the linear model, you have made some assumptions which were presented to you in class that you need to always check after you build your linear model. So it's okay if you build a linear model based on the observation that the plot of the data set seems to be following a linear trend, but then you need to check the assumptions and justify the use of a linear model, basically. So one of those assumptions, the first one, is independence. The first one that I will address is independence, which basically depends on the context, on the experiment itself. Now, this can be subjective, but usually if you think about the context of the nature of the situation, then it will be clear whether the different observations are independent from each other. Now, there was one example in the homework that I want to point to. It was about a league of some number of football games. I think there were like 20 games or 20 teams. I don't remember exactly. But that was an example, a very good example of when the independence assumption is not satisfied, because the different observations are not independent of each other, which means that the residuals are also, the error terms are not independent of each other, because if one team loses, then the other one wins. Okay, so that's about independence. It will usually be very straightforward to conclude whether this assumption is satisfied or no. Next, the linearity condition can be checked again. So we kind of check the linearity condition before building the model by observing the plot of the data set, but formally you need to check it after you build your model again. And I want to note here that linearity can also be checked by observing the plot of the residuals. The data set, the plot of the scatter plot of the data, is officially the way that you check the linearity condition, but also you can check it in the plot of the residuals. So if the plot of the residuals, if the residuals are evenly spread above and below the line at 0, then that means that we have a linear trend. And if there's no obvious pattern. Then the other assumption that we should watch out for is the normality assumption. This basically assumes that the errors or the residuals of the model are normally distributed. For this, we want to use either the histogram or the QQ-norm command. So we have two different ways of checking this. The residuals of the model can be obtained just by using this command, resid, and then of the model. So basically, when we plot the histogram, we want to observe a bell-shaped curve, or a bell shape in general, which needs to be unimodal, so it needs to have one peak, and then it needs to be symmetric. Now, in here, we can see that it is indeed unimodal, but it's not necessarily very symmetric. We can see that it's skewed. So just to double check, it's always a good practice to check both of these, to check normality in both of these ways. And then the second way is the QQ norm plot, which basically, in which we want the points to follow a straight line, so a straight trend. We can see that it more or less follows a straight trend, but at the beginning and at the end of this line, the values depart a little bit. So it's really, when it comes down to these assumptions, it's always to some extent subjective. So for this criterion, I would say it's satisfied. However, I do believe that for for exams and such, you will have examples that will be easy to decide on if you have these in mind, the appropriate tools. And then the last assumption that we want to check for is the equal spread. This assumes that basically the variance of the residuals and or the errors, which we are estimating by calculating the residuals, have an equal spread. So this means that throughout the linear model, the linear regression line, the observations are evenly spread above and below the line. Now, as I said before, we can obtain the residuals of the model with the resid command, and here I save them as residuals. And then there's one point that I want to note here, which is very important. When you plot the residuals, you always want to plot them against the predicted values of the model. So the reason for this is that there are some instances where if you plot them against just the y values, or just the x values, or just against an index, you might miss some trends or some patterns that you would otherwise observe if you plot it this way. So we obtain the residuals, and then we can obtain the estimated value. So this is basically the prediction. So at every value of x that we have, or the value of the predictor variable, we obtain the value of the response variable on the regression line. So the value that lies on the regression line that is estimated by our model. And then we simply plot it. So once we plot, we can see that the zero line is right here. We can see that the equal spread condition here is not satisfied, because at the start, most of the residuals lie above this line, so most of the residuals are positive. And then in the middle, the equal spread condition does seem, so it seems like the residuals follow an equal spread, but then at the end again, there seems to be more residuals below the line, so more negative residuals. So in general, the equal spread condition here seems to be violated. So now the last couple of things that I want to go over are the prediction intervals. First, let's take a look at a simple prediction. So basically, we want to calculate what the predicted MSRP is in our case, given a value of the wheelbase, and we can do that in the following way. So we use the predict statement, and then inside the parentheses we write first the model name, and then comma we write always list, and then inside those parentheses we write the name of the variable that we are given a value of equal to the value of that variable that we are given. So this will produce the wanted estimate. Now I did not mention before, but I want to go back to this line right here, line 489. If you just write predict and then the name of your model without anything else inside the parentheses, this will give you exactly the estimated values for every value of the predictor variable that you have. So just take note of that. So if we run this, then right here we can see that's the prediction, the predicted, or it's better to say the estimated MSRP for a given wheelbase of 45.5. Now, the next thing that we want to go over is the confidence interval. Just to go over what it means, or to reaffirm your understanding of the confidence interval. So the confidence interval always has to do with the population mean. Whenever you have a confidence interval with some certain with some level of confidence, you can say that with that level of confidence, the population mean will lie in between the two values, the extreme values of the confidence interval. So how we construct the confidence interval in R is very simple, just using the same command, and then inside the parentheses we have the same. So the name of the model, comma, then we give the value of the variable that we want. So in this case we want a confidence interval of confidence interval of values when values of MSRP when wheelbase is 45.5, and then interval equals to confidence. So in this case, we are obtaining basically the average value of MSRP when wheelbase is 45.5, or the mean of MSRP, you can think about it, when wheelbase is equal to 45.5. Now, if we run this command, we can see that it outputs this. So first we get the fit, which is the prediction or the estimate that we got before with the previous command, and then we get the lower and the upper bound of the interval. And the last thing is the prediction interval. The prediction interval tells us that there's a 95%, so a 95% prediction interval will tell us that there's a 95% chance that a wheelbase with with a wheelbase of 45.5, we will have an MSRP of value in between the two extreme values of the interval. So basically, the command that we use in R to construct the prediction interval is exactly the same as the one for the confidence interval, but instead of confidence inside the quotation marks, we put prediction. So once we run that command, we see that we get another interval here. So basically, the way to interpret this prediction interval is to say that there is a 95% chance that when we have a wheelbase of 45.5, we will have the MSRP lie in between these two values. There's one other thing that I would like to mention before I conclude this video. Prediction and confidence interval is by default 95%, so 0.95. If you want to change this, you can add another part inside the parentheses here, which is done in the following way. So you write level equals to, and then 0.95 or 0.90 or whatever your desired level is of the interval.